An alternative definition of acids and bases is the Bronsted-Lowry definition of acids and bases, and that's what we'll be studying in section 10.2. According to the Bronsted-Lowry definition, an acid is a substance that donates protons or donates hydrogen ions. So we can see this in the following equation. When HCl gas is bubbled through liquid water, one proton or hydrogen ion is transferred from the HCl gas to the water. This gives us chloride ions and the hydronium polyatomic cation. Now the good news is that anything that's an Arrhenius acid is automatically a Bronsted-Lowry acid. So if you recognize it as one, it's automatically the other. In the Bronsted-Lowry model, the definition of a base is it is a substance that accepts hydrogen ions. So if I take some ammonia and dissolve it in liquid water, then protons or hydrogen ions will move from the water to the ammonia. This gives us the ammonium cation and the hydroxide anion. So there we go, all right? So it's important to recognize that when an acid ionizes in water, it is the water that is functioning as a base, right? So the previous reaction that we had, hydrogen ions were going from the hydrogen chloride to the water. Water is functioning as a proton acceptor in this case, so it's a base. So it's interesting, the water up here is functioning as an acid, as a proton donor. And we'll come back to this, but it seems that water can function as an acid or a base depending on what it's being reacted with. So here's an example from the book. It says aniline, and it gives the formula, is slightly soluble in water. It has a nitrogen atom that can accept a hydrogen ion from a water molecule, just like the nitrogen atom in ammonia does. Write the chemical equation for this reaction and identify the Bronsted-Lowry acid and base. So C6H5NH2 is going to accept a proton or a hydrogen ion from water. That's going to add a hydrogen ion to the aniline and take a hydrogen ion from the water. So the water is functioning as the proton donor and the aniline is functioning as the proton acceptor. So the water is the acid because it donates the proton, and the aniline is the base because it accepts the proton. Okay, here's where it gets a little weird. We learned in chapter 9 that reactions can go both forwards and backwards, that it's possible to establish an equilibrium. So consider the reaction of the weak acid of the acid HNO2. It's going to function as a proton donor when dissolved in water. This will result in the formation of the hydronium polyatomic cation and the nitrite anion. Now let's think about what happens in the reverse reaction. In the reverse reaction, the opposite occurs. A proton is transferred from the hydronium ion, making it the proton donor or the acid, and the nitrate anion functions as a base or proton acceptor. This regenerates the water and the HNO2. So what we can see is that an acid reacts with a base to produce a new acid and a new base. You see? So that's kind of interesting. So in the Bronsted-Lowry model, an acid dissociation reaction is described as occurring between acid-base conjugate pairs. So returning to our example, here's our acid HNO2. It's reacting with our base, our proton acceptor. A proton moves from the acid to the base. This produces a new acid, the hydronium ion, and we call this the conjugate acid. And it produces a new base, the nitrate anion, which we call the conjugate base. So, in the Bronsted-Lowry model, the acid dissociation is described as occurring between a pair of an acid and its conjugate base, and a base and its conjugate acid. So a conjugate acid-base pair of this type are two things that differ by one proton. So here are some examples. We have HCN and Cn minus, H2CO3 and HCO3 minus. And you can see that each member of this pair are just different by one H plus. It should be noted that the acid is the species that always has the additional H plus. Here's another example. We have a base, and then when we add the proton, we get the conjugate acid. We have the hydroxide ion, it's the base. When we add a proton, we get water, which is its conjugate acid. So a conjugate acid-base pair are simply two things that differ by one proton, and the acid always has the extra proton. Here are a couple of examples of an acid and a base being dissolved in water that allow us to see what we mean by conjugate acid-base pairs. Notice that the acid and the base are always on the left of our equation, and the conjugate base and conjugate acid are always on the right. The proton always moves from the acid to the base, generating the conjugate base and the conjugate acid. Here's one where it's not a base in water, but rather an acid in water. You can see the same thing. We have an acid and a base on the left of our arrow, and we have the conjugate acid and the conjugate base on the right. The proton moves from the acid to the base, generating the conjugate acid and the conjugate base. So let's have a look at this example. It says identify the conjugate acid-base pairs in this example. So here we have an acid. It's going to donate a proton to water. That makes the hydronium ion, and then it also makes this anion here, which is called the acetate anion. You'll learn about that in a little while. So on the left, the proton donor is the first reactant, so we're going to call that the acid, and the proton acceptor is the second reactant, water, and we're going to call that the base. The conjugate acid is the thing that has one more proton than the base, and the conjugate base is the thing that has one less proton than our acid. So our conjugate acid-base pairs it's going to be one pair, and then our other pair is going to be like that. Okay, so acid, conjugate base, base, conjugate acid. You can see the only difference between these guys is one H plus. Okay, and that concludes our section on the Bronsted-Lowry definition of acids and bases.